Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray that you bless our work today. Just help us to glorify you in what we do, Lord. In your name I pray. Amen. So let's see here. We have been talking about how to solve the problem of systems of differential equations, right? And so what we talked about yesterday in a fair amount of detail, I think, is how to solve, let's say, dv dt equals to AV, where A is n by n real matrix, right? And so just to kind of bring it together, the thing we did mostly to yesterday was, number one, we looked for eigensolutions, right? Basically things of the form v equals to e to the lambda t times u, where a minus lambda I u equals to 0, and the determinant of a minus lambda I is equal to 0. Of course, we had u not equal to 0, right? And as we discussed, there's some substructure there, right? We either have lambda is a real. If lambda is in the reals, then v equals to e to the lambda tu is it, right? But if lambda is in the complex numbers, in the sense that we have lambda equals to alpha plus I beta, with beta not equal to 0, then the v equal to e to the lambda t u gives us, after the dust settles and we settle our notation and all that, we get two solutions, right? We get e to the alpha t cosine beta ta minus sine beta tb, and e to the alpha t sine beta ta plus cosine beta tb, right? So that was just the eigencase. These are our solutions. We either get, for each real eigenvector, we get an eigensolution, and for each complex eigenvector, we get a pair of real solutions, the real and the imaginary part, right, of the complex solution. So that was part number one, right? But then we learned that some matrices don't have enough solutions, right? Because our general goal is to construct the general solution, and we need n linearly independent solutions to do that, but there's not enough with just what's here in part one, right? So 2, we introduced the matrix exponential. We saw that e to the ta, which is I plus ta, plus 1/2 t squared a squared, plus dot dot dot. I mean, if you want me to write it more carefully, it's the sum n equals 0 to infinity of 1 over n factorial t to the n, a to the n. So this is the matrix exponential. And we studied that at the end of class yesterday. We learned that this is a solution matrix, and it's invertible. In other words, that this is a fundamental solution matrix. The critical things is that the derivative of e to the ta is a e to the ta, right? And the determinant of e to the ta is not equal to 0. So in short, x equals to e to the ta is a fundamental solution matrix. And I showed you one example of how we could calculate it if the matrix was relatively simple, right? But now this is our task, is to understand what is this fundamental solution matrix, the matrix exponential. We should also try to answer the question, how does that fit together with what we already learned in part 1, right? And how do we actually calculate with the matrix exponential? So I'm going to try to explain that to you in the next hour or so. I'll start with an example, right? Before I get to the example, I really should just remind us what's our general theory. Our theorem is basically this. If we have dv dt equals to AV has fundamental solution matrix, say big X, then V equals to big X times C, right, is the general solution. Now let me try to unpack that for us a little bit. Here's a proof. Because I didn't show you the proof yesterday, I just claimed it, So if we let x equal to x1, x2, and so forth on down the line, xn, like that, right? Suppose that this matrix is formed by these n columns, x1 through xn, right? So what does it mean to say dx dt? What is dx? Well, dx dt is what? It's dx1 dt, right? dx2 dt. Down the line, dxn dt. So we differentiate component-wise, right? So the derivative of a matrix is also the matrix of the derivatives of its columns. Now, if we're assuming that X is a fundamental solution matrix, what's that mean? We have that this is equal to, what is it equal to? Since it's a fundamental solution matrix, this is equal to A times big X, right? Which, by the way, solution matrix. But this, right, guys, is A times x1, x2, xn. One of the things I told you in the start of our discussion of matrix math is that you can either multiply matrices as a bunch of dot products, right? Or you can do it column by column. So the column by column matrix multiplication says that, hey, this is actually the same as A times x1, A times x2, A times xn. This is a pretty simple proposition from linear algebra. You can work it out. I often assign this as a homework problem in linear to show that what I just did makes sense. All right, it does make sense, though. And so what we have then, if you compare, we have this matrix equation, right? We have that this is equal to that. So two matrix equations are equal only if every component matches up, right? So you can read from this single matrix equation n column equations. We have to have the first columns match. What does the first column matching give us? This has to equal that. What's that tell us? What's that say? That says that the first column of the solution matrix is a solution to the differential equation, right? It's a vector of functions, which when you differentiate it, it gives back the system. I mean, it works. And likewise, it's the same for each one. So you can see that for j equals 1, 2, all the way out to n. Then what did our theorem say? I didn't prove it, but I stated it for you. What would the general solution look like for a homogeneous problem? Remember, it was x equals to c1 x1 plus c2 x2 plus plus cn xn. Well, you can take this linear combination and you can rewrite this simply as x1, x2, xn times the vector c1, c2, cn. In other words, this is x times c. So the linear combination of these solutions, x1 through xn, can also be written as the matrix with x1 through xn glued together times this column of constants. So we have choices in terms of notation. We can either say the general solution is, this linear combination c1x1 plus c2x2 da, 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 plus cn xn, or we could say it's the fundamental solution matrix times a vector of constants. These are just two different notations for exactly the same idea. All right? So you guys, I want you guys to tell me, what is this? If I take, what is this, though? Ooh, sorry, no vector here. What this is a linear combination of columns of x. Just a remark, okay? So, e to the at, or e to the ta rather, is the fundamental solution matrix, right? So if I multiply e to the at times any vector, what do I get back? I get a linear combination of the columns of the matrix exponential. But this is a homogeneous problem, right? So the linear combination of solutions is, again, a solution. So application, if I say e to the ta times any constant vector, really times any vector, let's say u, solves the dx dt equals to ax. Do you see that? See, because if I take the matrix exponential and I multiply it by a vector, that's just a linear combination of the columns of the matrix exponential. So it's, again, a solution. You guys with me? All right. This is important because we use this idea in pretty much everything I'm doing today. So example 1, just take a step back here and just calculate a matrix exponential. Suppose we have a equals to, let's say, 2, 3. 2, 0, 0, 3. It's a pretty simple matrix. What's a squared equal to? What happens when we multiply a diagonal matrix by itself? Some of you guys have had 221 already, so this should be like, you should know this. Like, somebody wakes you up from a deep sleep and they go, square of a diagonal matrix. You should be like, it is just a diagonal matrix with the squares at the diagonal. Like, it should just be instinctual. You just square the diagonals, right? This is 2 squared, 0, 0, 3 squared, right? And if you keep going here, it just so forth and so on, right? Like, a to the n power is 2 to the n, 0, 0, 3 to the n. In this case, it's pretty simple to see that. So we can calculate the matrix exponential here directly from the definition. It's kind of fun. So this is the sum, n equals 0 to infinity, of, what do we say, t to the n over n factorial, a to the n. Well, what's a to the n? A to the n is 2 to the n, 0, 0, 3 to the n. Okay? And then what we can do is we can rewrite this as a big matrix. It's got the sum n equals 0 to infinity of t, well, we can rewrite that as 2t to the n over n factorial, 0, 0. Sum n equals 0 to infinity of 3t to the n over n factorial. See, because, for example, 2 to the n, t to the n is equal to 2t to the n. Right? And the series of a matrix is the matrix of the series. If you work on the analysis, that's how it goes. Anyway, there's some analysis here. I'm kind of, you'll forgive me if I don't prove convergence and stuff like that in here. This is a meaningful calculation. I haven't proved it. Anyway, so this, what is this and that? Can you recognize what those are? No one said calculus 2? Or it's just too far away? I mean, these are the power series for the exponential, right? Like what's e to the x? E to the x is the sum, n equals 0 to infinity, of x to the n over n factorial, right? So put x equal to 2t, or put x equals to 3t. That's the exponential of 2t, and 0, and 0, and e to the 3t. So the point here is the exponential of a diagonal matrix is actually the matrix, is again a diagonal matrix where the diagonals are the exponentials of the original matrix. Let me write it down in general. So example lemma, basically extrapolating from example 1, we have the following. If you take the matrix exponential of, say, d1, d2, dn, right? Then it turns out, through a very similar calculation to the one we just did, that this is the same as e to the d1, e to the d2, e to the dn. So on the left-hand side of this equation, I'm talking about the matrix exponential. On the right-hand side of that equation, I have an ordinary matrix with exponentials, just from like calculus 1 or pre-calculus even, right? Good? Make sense? No? Yes? All right. Okay, so example 2. What if we have a times u equals to lambda u, right? What happens if I multiply this by a? What's a times au? Lambda is a constant, right? So we can pull it out. So what do I have here? I have a squared on the left-hand side, right? What happens when we hit au again? We get what? We get lambda lambda u, right? What's lambda lambda u? It's also known as? You guys are killing me. Lambda squared u. In my heart, I know you guys can understand what I'm saying. Should I start class with donuts or something? Would that help? But it's so hot. I feel like it might lead to intestinal distress. I don't know. It's not too bad right now. What am I complaining about? Today's pretty nice. And what happens if we do this? I think you see where I'm going with this, maybe. What's a cubed times u going to be equal to? You just multiply both sides of a here. You get what? You get lambda cubed u, right? See what's going to happen here? So, all right, so we have these identities. What happens then if we take e to the ta, right, and we multiply that by u? What's that going to be equal to? What's going to happen when we multiply the matrix exponential by an eigenvector? What happens? We've got I plus ta plus 1/2 t squared a squared plus ... right? So if you apply my lemmas, what do we got? We got u plus t lambda u, 1/2 t squared lambda squared u, 1/3 factorial t cubed lambda cubed u. If if you look at this, there's something we can factor out, right? There's this u on everything, right? So we can factor out the u vector. In fact, we can, this is just a scalar multiple of the vector u. What's the scalar multiple, though? There's a 1, right? Plus t lambda. 1/2, t squared lambda squared. 1/3 factorial t cubed lambda cubed. Can you recognize what that is? What's that? No. I mean, if lambda was I, it could be cosine plus I sine t, sure. But generically speaking, what's this? It's the same pattern as these, but with instead of 2 or 3, it's got lambda. I mean, this is e to the lambda t. Wait a minute, what is that? Aha! So the matrix exponential gives us back everything we found in part 1 of yesterday. If we take the matrix exponential times an eigenvector, we get back the eigensolution again. See? They're there. Right? Remember, this was the solution that we found for the most part yesterday, right? And this calculation, by the way, still makes sense when u is complex, right? Lambda is a complex eigenvalue, u is a complex eigenvector. This would still be a complex solution. That stuff still makes sense here. Okay. All right, so that doesn't, I mean, that's great, but that doesn't get us to anything new, right? To get to new things, we need something called the magic formula. So let me derive the magic formula for you. It's kind of a chicken or egg thing. From a pure math perspective, you might say, well, the magic formula only makes sense once you know about something called a Jordan basis. But on the flip side, I think discovering the magic formula shows you why you want to look at a Jordan basis. That's kind of more the direction of thinking in here. So we're going to start with the magic formula. So let me just get right to it. So e to the ta. And so what I'm going to do is this calculation is very much based on the last example of last class. I actually did the magic formula for basically for a specific matrix, the same series of calculations as I did there. So what I'm going to do is I'm going to do t times a minus lambda I plus lambda I. So I added 0, right? Now, this is going to be e to the t times a minus lambda I times e to the lambda it. Now, the reason I can do that is that lambda I commutes with t times a minus lambda I. How do I know that? Well, lambda times I, that's a scalar multiple of the identity matrix. The identity matrix times the number, that will commute with any other matrix. So in this particular case, I have e to the a plus b is e to the a times e to the b. It goes back to that. These matrices commute, so I do have laws of exponents here. Now so let me, and you can see that I could just as well have, you could add lambda I here, or you could, let me just for the sake of not introducing an extra step here, lambda I plus a minus lambda I is better for me, because then poor planning on my part. Sorry, guys. So we could just as well have put the e lambda I t here and e to the t times a minus lambda I there. That's, you just make that your next step. These commute as well. Okay, now this is what? That's the exponential of lambda t, lambda t, dot, 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 lambda t. That's the exponential of a diagonal matrix. I'll leave the other one alone. What is the exponential of a diagonal matrix, though? It's the, what is it? It's e to the lambda t, right? E to the lambda t. E to the lambda t, right? So it's this kind of boring matrix, this diagonal matrix where we have e to the lambda t every entry of the diagonal. If that's the case, then you can factor out that constant to the front, right? So this thing right here, that's really just e to the lambda t times 1, 1, da, 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 1, right? This is the identity matrix. So this, in fact, is just equal to e to the lambda t times e to the t times a minus lambda I. All right? Which is pretty awesome. I mean, that's better. And then I just write out what that means. So this is e to the lambda t times the identity matrix plus t times a minus lambda I plus 1/2 t squared a minus lambda I squared plus so forth and so on. So this right here, I'll box it in just a second, is what I refer to lovingly as the magic formula. The reason I call it the magic formula is because it's where the magic happens. I mean, with the magic formula in hand, we can understand example 2 in a new light. Here's what example 2 looks like with the magic formula. We take e to the ta times u. That's equal to e to the lambda t times I plus t times a minus lambda I plus dot, 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 dot times u. What goes on there? Remember what we said yesterday? We said that AU equals to lambda u is interchangeable with a minus lambda I times u being 0, right? That's just another characterization of an eigenvector with eigenvalue lambda. So what happens to this a minus lambda I u term? Assuming that u is an eigenvector. This gone. This is 0, right? And the situation only gets worse for things higher up in the magic formula, because like next I've got a minus lambda I squared times u. Well, the first copy of a minus lambda I, which hits u, makes it 0. So the series truncates, chop, 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 and all that's left is this first term. I times u is u again, so we just get e to the lambda t times u. Now, I think the derivation I did in black is more natural for you guys, right? But I think it's also useful to see how the magic formula reproduces example 2. Does that make sense? I mean, you can agree or disagree. All right, so at this point, I need to drop some, I need to tell you one of the central theorems of linear algebra, which is seldom and sadly hardly proved. And you know, you could look across the land for a linear algebra course where this is actually proved in the first course, and you'd have a hard time finding it these days. And that's really unfortunate because you know, this thing I'm about to tell you is actually kind of the pinnacle of linear algebra. It's really useful for applications, and it's kind of important. But there's this theorem which says that if A is a real matrix, let's say with real eigenvalues, just to keep it simple to start with, okay? Then there exists a Jordan basis for A. And a Jordan basis for A is basically, that is a basis for Rn made of generalized eigenvectors arranged in chains. So I guess I should probably define for you generalized eigenvector, right? So if here's the deal. If A minus lambda I, all right? If this to the p power, all right? If this to the p power times u is equal to 0, all right? But A minus lambda I to the p minus 1 power u is not equal to 0, all right? So this is for p greater than or equal to 1. Then u is a generalized eigenvector of order p with eigenvalue lambda for A. A lot of strings attached there, isn't there? The point is this vector u, its mission is to serve A, to describe something about the structure of the matrix A. The chain is something like this. We have, let's say, u1, u2, dot, 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 let's say uk. And the way it works is that A minus lambda I times uj is equal to uj minus 1 for j equal to 2, 3, all the way out to k, and A minus lambda I times u1 equals to 0. If you have vectors which satisfy this chain condition, it will make them generalized eigenvectors. Now, let me not be so abstract. Let me give you an example. That will help. Oh, by the way, this is descriptive. I don't expect to give you like an arbitrary matrix and then say, hey, go find a Jordan basis for it. I don't sometimes ask 321 that question. That's a hard question. That's really more a graduate linear question. Well, I don't know, it depends, but this is something we want to use. I typically will provide either a matrix which is pretty simple, so it's easy to find such a basis, or I will provide you sort of the abstract setup. This is for us mostly a language. It's not a problem type we're going to learn how to solve. It's something we're going to use to solve other problems. So where am I? Example 3. If we look at the matrix 3, 1, 0, 0, 3, 1, 0, 0, 0, all right? Then, oh, not 0. I meant to put a 3 down here. Sorry, guys. I claim that U1 equals to 1, 0, 0, U2 equal to 0, 1, 0, and U3 equal to 0, 0, 1. These are going to form, in fact, a chain of generalized eigenvectors. All right. So check it out. What's A minus 3i? What's A minus 3i? 0, yeah? 0, 1, 0. I think 0, 0, 0, 0, 1, yeah. So subtracting 3 times the identity just removes the 3's from the diagonal there. Okay, so if we look at A minus 3i times U1, that's what? That's 0, 1, 0, 0, 0, 1, 0, 0, 0 times 1, 0, 0, which is, by the way, 0. What happens if we look at A minus 3i times U2? What does that give us? What happens when we multiply this matrix by 0, 1, 0? We get 1, 0, 0, I think. What's that? It's U1, right? Okay. What's A minus 3i times U3? Zero, 1, 0, right? Also known as U2. So you guys tell me, what is U1, what is U2, what is U3 in terms of this definition I just wrote over there? First of all, what is U1? Can you guys tell me? We have A minus 3i times U1 is equal to 0, right? I mean, this is entirely the same as saying that A times U1 is equal to 3U1, right? It's a what? Okay, so it's agreed you guys are not going to answer questions. I mean, we should just settle this. I'm not playing poker with you guys. So this is lambda equals to 3, right? I mean, U1 is an eigenvector, right? So a generalized eigenvector of order 1, by the way, is just an ordinary garden variety eigenvector. How about this U2? What happens if we look at, now clearly, A minus 3i times U2 is U1, which is non-zero, right? What happens if we look at A minus 3i squared U2? What's that equal to? Right, so this is U1. So what's A minus 3i times U1? Zero. So we have the situation that U2 is generalized eigenvector order what? 2 with eigenvalue 3. How about this U3? What happens if I look at A minus 3i cubed times U3? What's that give me? That gives me A minus 3i squared times U2, which gives me A minus 3i times U1, which gives me 0 again. But on the flip side, what's A minus 3i squared times U3? A minus 3i squared times U3 is U1, which is non-zero, right? So U3 is a generalized eigenvector of order 3 for eigenvalue 3. So this is an example of a Jordan basis. In this case, U1, U2, U3 is a Jordan basis for A. In fact, A is is already in what is called Jordan form. Jordan form is like the next best thing to diagonalizability. It's as close as you can get to diagonal. You can't diagonalize this matrix, as it turns out. All right, so with the Jordan basis in hand and the magic of the magic formula, we can now write down the general solution to such a problem. So let's, example 4, use the chain conditions to make magic formula come to life, let's say. I don't know. So here we go. E to the TA times U1. By the theorem I just erased here. By example 2, what do we already know? U1 is an eigenvector, eigenvalue 3, right? So this is just e to the 3t U1, right? By example 2. Now U2. E to the TA times U2. How's that go? Well, we've got e to the 3t times I plus t times a minus 3i plus 1/2 t squared a minus 3i squared plus dot, 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 all of that times U2, right? What I just wrote, I don't usually write. I'm just writing it to try to emphasize the logic here. So this is the magic formula. Like, the magic formula, does it tell you what lambda is? I mean, the thing is, this derivation I did for the magic formula, it's good for lambda equals to 3. It's good for lambda equals to 17 plus 13i. It's good for any lambda. It's just when you choose lambda as an eigenvalue for the matrix, then you get the Jordan basis, which allows you to truncate the magic formula. And just, that's where the beauty is. Let's see here. So 3t ut, I times u2 is u2 again, right? So what happens to the last term I wrote, a minus 3i squared times u2, we've just argued that that was 0, right? And guess what? Everything beyond it, it's all zeros. Do you understand why that is? All the higher things that I haven't written have an a minus 3i squared in it and more, right? Like a minus 3i cubed, it's a minus 3i times a minus 3i squared. So when that hits u2, it's still 0. And so forth and so on, all the way up the line. Does that make sense to you guys? If it doesn't, just interrupt me, please. How about this? What's a minus 3i times u2? That's u1, right? So we get e to the 3t times u2 plus t times u1. So let me say this is part 1, this is part 2, let's do part 3. What happens when we hit e to the ta times u3? We have e to the 3t times u3 plus t times a minus 3i times u3 plus 1/2 t squared a minus 3i squared times u3, 1 over 3 factorial t cubed times a minus 3i cubed u3, and stuff. I mean, the last thing I wrote, if we really understand what's going on, we don't even need to write, because as we know, u3 is a generalized eigenvector of order 3, which makes this term go sploot. It's gone. How about a minus 3i squared times u3? What's that? We worked that out over here. That was u1, right? And what was a minus 3i times u3? Well, by the chain condition, that was u2, wasn't it? So what we get is e to the 3t times u3 plus t times u1 plus 1/2 t squared. Oh, I'm sorry, that was u2. tu2 plus 1/2 t squared u1. So I can write the general solution then now, right? So x is equal to, I guess I was using v? I guess I haven't really said. Let me write it down. So to this, the solution of dv dt equals to av is generally v equals to c1 e to the 3t times u1. In this case, u1 was 1, 0, 0, plus c2 e to the 3t times what? What is this actually? This is e to the 3t. This is actually t, 1, 0, I think. Do you guys agree? Because u2 is 0, 1, 0, and u1 is 1, 0, 0. So if you add those, we get t, 1, 0. So we get t, 1, 0, plus c3 e to the 3t. And this one is what? This is e to the 3t times, looks like 1/2 t squared, t, and 1. And there you go. That's the general solution built from the matrix exponential. Thoughts? Prayers? I mean, no? All right. big idea here is, if we can find, or if somebody gives to us, a Jordan basis for the matrix, right? Then we can take the chains of generalized eigenvectors. We can use the magic formula with the eigenvalue that's attached to the chain, and then hit the vectors in the chain. When we do that, the magic formula truncates, and we're just left with things like this, or our handy-dandy eigensolutions from last time. There's always an eigensolution at the start of every chain. And as you go up the chain and get to higher and higher order generalized eigenvectors, you pick up higher and higher powers of t. So like if I had an generalized eigenvector of order k, I would get a t to the k minus 1 in one of the components of the solution. So this is how systems of differential equations pick up solutions that involve multiplication by t, or t squared, or t cubed. It's unfortunately not so simple as just multiplying the eigensolution by t, right? Again, just to make the point, it's not that we take the eigensolution and just multiply by t, right? The next solution up the chain has t appearing here, but not here. And the next one past is not just multiplication by t squared. There's a 1/2 t squared here, there's a t here, there's a 1 here. And the fact that these solutions look pretty nice is just in part because the chain here is so simple. It's just the standard basis. These are the very nice vectors, right? This is pretty much the neatest possible presentation of this kind of problem. It really can't get simpler than this. If these vectors were uglier vectors, right? If they had lots of non-zero numbers in them, then these formulas would be likewise uglified, right? Now, for an in-class test, I don't ask you to solve these from base principles, except in like the n equals 2 case. Order 2 we can do. So we should do one of those. Let's see here. See if I can find one of those right quick. So I guess a fair amount of what I'm telling you is in section 9.8, but I do think I bring something a little bit past what's in 9.8. All right, so 1 minus 1, 1, 3. All right, so first of all, we figure out the eigenvalues. Okay, so we have a repeated eigenvalue of 2 in this case. For a 2 by 2, it pretty much means we're going to need to use the matrix exponential. In like the 2 by 2 case, it's either a diagonal matrix, so there are 2 eigensolutions, or it's not, in which case we need to use the matrix exponential. All right, anyway. So what's a plus 2i? We got a 3, we got a minus 1, we got a 1. What? Did I do that wrong? Oh, so lambda equals 2, so I'm supposed to do what? Lambda, a minus lambda I, right? I was about to get, like, this, so this is actually a good learning experience. Like, you write this down. You should be like, uh-oh, flag on the play. That's an invertible matrix. The determinant of this matrix is 15 plus 1. The determinant 16. This has an inverse. It corresponds to independent equations. This means I made a mistake. Where was my mistake? Right here. See, I'm supposed to do a minus lambda I, right? Here lambda is 2. So I'm supposed to have a minus here, right? Putting a minus here makes this not 3, but minus 1, and makes this not 3, but 1. And then you can see, oh, okay, good. So let's see here. So we have a minus 2i. I didn't write that down. I'm sorry. What's my eigenvector? You guys tell me. So basically, if I have a minus 2i times uv equals to 0, 0, that says to me that u plus v has to be equal to 0, right? So u has to be minus v. So if I set v equals to 1, I get u1 equal to minus 1, 1. There's an eigenvector with eigenvalue 2. Then I take a minus 2i u2 equals to u1. All right? Let's see if I can solve this. If I can solve this, this will give me a generalized eigenvector order 2. All right? So let's see here. That's actually just what? That's, again, minus 1, 1, 1. uv equal to what? Minus 1, 1, right? So to find the generalized eigenvector, I have to solve the equation what? This is, again, the same equation 2 times. We've got u plus v equals to 1. Right? Many choices. I personally like to put v, I'm just going to set v equal to 0, and that will tell me that u is equal to 1. So my generalized eigenvector order 2 is going to just be 1, 0. Okay? And then following basically the same song and dance we just did with the magic formula, I can write down the general solution. So x equals to c1 e to the ta u1 plus c2 e to the ta u2. And when you do the magic formula, what you're going to get is c1, what was my, e to the 2t, u1 plus c2 e to the 2t times u2 plus t times u1. To be more explicit, c1 e to the 2t minus 1, 1, c2 e to the 2t 1 minus t, and then t down here. And there you go. That's the general solution. The matrix exponential picks up that second solution we were missing in our previous way of thinking. All right, well, we can stop here. You can ask me further questions about this when we get back from the break. Take a little 10-minute break here. We'll start again. So we'll start again at 12:05.